So I'm in Antarctica right now, in West Antarctica. I'm supposed to be doing a sea ice campaign this winter. It's winter in the southern hemisphere, but the conditions are terrible. And one reason that they're terrible is because sea ice conditions are actually terrible in the whole hemisphere. So here is a graph of the sea ice extent this year, the area that sea ice covers, and 2023 is really sticking out like a broken bone. It is very poor, even compared to last year, which in itself was record breaking. And people are trying to contextualize quite how bad it is on Twitter, but also in the news media, by talking about it in terms of sigmas. And I think that is good, and I'm going to explain what a sigma is soon. I think that's nice because it plays into people's understanding from the news media of particle physics and certainty, but people are also explaining how bad the conditions are this year with reference to a 1 in 7.5 million year event. And I guess I disagree with that, and I'm going to explain why. I think that statistic makes people sit up and take notice, but it comes at the cost of our statistical credibility. That number is kind of pulled out of a very large number of very bad assumptions, and I'm just going to go through those and try and explain why I don't think that number is very rooted in confidence. So first, I'm going to introduce what is mathematically well defined, but actually really hard to conceptualize, a standard deviation. And all I'm going to say is a standard deviation, a sigma, 1 sigma, is a measure of spread. And basically, the larger a standard deviation is, the more spread out you think some data are. So people will tell you, they'll talk about the 68-95 rule, and a lot of people will tell you that, well, one standard deviation either side of the mean captures 65% of the data, and 2 standard deviations either side of the mean will capture 95% of your data. But that is actually only true for what we call a normal distribution. And I guess I would discourage that in this scenario because there's not very strong evidence that we actually live in a normally distributed world of Antarctic sea ice. So for now, I'm just going to say it's kind of interesting to talk in terms of standard deviations away from the mean, and it's important to remember that standard deviations actually are not related to the normal distribution. They don't depend on ideas of statistical distributions. So let's plot today's sea ice. I should say I'm recording this on the 31st of July, and I have data from the up to the 30th of July on my computer. That is the 211th day of the year. So that is where this red line goes up to, and let's plot it as relative to the 1 standard deviation range, which some people will tell you captures 68% of the data. I will refrain from committing to that, but it's certainly very serious, and we're wildly out of the typical range, whether that be 68, 80, whatever percent. We're well out of the typical range of variability in Antarctic sea ice. Something serious is going on here. And you can actually plot more than the 1 sigma range, the 1 standard deviation range. You can plot the 2, 3, 4, 5 standard deviation range. And it turns out we're actually beyond the 5 standard deviation range. We're somewhere between 5 and 6 standard deviations away from the mean on the 211th day of the year, which this year is July 30th. So very serious, and this is what people mean when they talk about standard deviations away from the mean, why we're experiencing a 5 sigma event or whatever. Here is a graph of how that has evolved. So you can see that we started the year on the 0th day of the year, January 1st, and we were between 2 and 3 standard deviations from the mean at that time of year. And then the anomaly in this formulation got smaller. It actually went below 2 standard deviations from the mean, and then it just grew and grew and grew and became more and more significant until we got to July, where it was more than 5 standard deviations away from the mean. And here is one criticism I have of this overall nice formulation of the situation, is that this kind of implies that we're going steady over the last 2-3 weeks, in fact. Actually, over the last month. It would imply that we're holding steady in standard deviations from the mean. But if you actually look at the anomaly in terms of how many million square kilometers we are missing from the mean, conditions have actually kind of improved. The anomaly has shrunk over the last month, and you might stroke your chin and ask why that has happened. How is it that we are hovering at about 5.5 standard deviations from the mean in this metric, but it looks like things are getting better over the last month in this metric, and that's my criticism, that the actual value of one of these standard deviations changes very significantly over the year. It in fact halves from early January, where a standard deviation is about 4/5 of a million square kilometers, and then over the last 2 weeks, a standard deviation has been 2/5 of a million square kilometers. So this is how, although the absolute size of the anomaly in million square kilometers is shrinking, this sigma thing that people talk about is staying steady. So moving on from sigmas, I think that's just an interesting aspect of this analysis. I'm going to move on, and I'm going to try and talk about the 7.5 million year statistic. So I've used climate change here, but we're going to ask the question: how likely was this to occur in a world that is, while we've been looking at the sea ice from space, 1979 to 2022, given the sea ice that we've seen, how likely is this freaky low anomaly to occur? And to answer this, you have to make a couple of major assumptions that we didn't have to make for the sigma analysis. Firstly, you have to assume a probability distribution. And secondly, you have to assume that is stationary. So the major one is you have to pull out of your pocket a probability distribution. People often just jump right to the normal distribution, which I think is a shame, because there are lots of other good ones out there. We can plot the historical data. So in blue, I've plotted the sea ice extent on July 31st in million square kilometers from 1979, which is when we got these satellites up in space, to 2022, so last year. And how likely is it that we, on yesterday, in fact, got this sea ice extent? And I put them in 0.5 million square kilometer bins if the nerds are interested. So you can see that it's most likely, based on historical data, to be between 17 and 17.5 million years. Million square kilometers. And there is a possibility that it is slightly less likely that it's between 16.5 and 17. And then it's significantly less likely again that it's going to be between 16 and 16.5 million square kilometers. So we have this like central 17 number that it's most likely to be based on historical data, and then it gets less and less likely as you move further away. And then we have this year that I've marked in dashed, 2023, where it's below 15 million square kilometers, and that is way outside of our historical experience, way outside of this histogram, this bar plot, and we can just jump back to that first slide. You can see that it's way outside of our experience. So, how far outside is it? And how likely, based on the data that form this histogram, were we to get a dashed line below 15 million square kilometers? So we're going to fit 3 different probability distributions to this. And I'm actually going to remove the numbers on the y-axis because they're kind of not that intuitive. We're talking about probability densities here, not actual probabilities. So I'm just going to bin those and say, look, when we fit the data, we get these 3 curves from these 3 different probability distributions, red, orange, and green. And they kind of look almost exactly the same, right? You often can't see the green one because it's like underneath the red and the orange. But if we want to ask the question, and I'm going to form this sentence carefully, how likely were we to see a sea ice extent of less than what we see now, or the same? What we need to do, the mathematical thing we need to do, is add up. If we say that the area under these curves is 1 each, like the number 1, what is the area of the curve to the left of that dashed line. And you might go, hey, the curve is actually 0 to the left of that dashed line, but it's not. It is a very small amount, but it is non-zero. And in fact, although these red, orange, and green curves look very similar in the area of the data, they vary wildly in their size to the left of that dashed line. They are hugely variable. The size of their, what we call the tails of this distribution, are very different. So therefore, the area under the curves to the left of that dashed line, while being very small in an absolute sense, it's like thousands and thousandths of a thousandth of a percent. They're frequently like 10 times the values of each other, millions of times the values of each other. So this is my point. The probability distribution that you fit to this is essential to calculate how likely we were to get such an extreme event. And it's extremely consequential to the number you get in the end. And we don't know, right? We don't know which one of these distributions actually fits this histogram. We have no idea. If I were to tell you that it's in fact a log normal curve, with any confidence, you should laugh at me, because like there is basically no difference in the area of the data. In the region that the historical data is in, these curves fit just as well as each other. So we can't decide between them. So I actually calculated, and it took a mighty toll on my computer, but I did calculate the area under each of these curves to the left of this 2023 dashed line. And sorry, that's my radio going off in the background. And the numbers are tiny. They're like a millionth of a millionth. And the way to calculate the recurrence time, so a 1 in 75 million year event, is to take what we call the reciprocal. So divide 1 by that tiny, tiny number, and you get a massive number, like 7.5 million. So here are the results. I'm going to show you a table of recurrence times, and you can treat each number like the million year event thing. So the first row is for the 201st day of the year. A log normal distribution gives you a 4 with 20 zeros behind it, which is it's over 1 million times the age of the Earth. But if you fit a normal distribution, it's more like 10 million. And what I did is to get some, like, these numbers vary a lot from day to day, with the 211th day of the year being yesterday's data. I just averaged them over the last 10 days to get the number that is the 7.5 million thing. And my numbers are, for a log normal distribution, it is a 1 in 1 with 29 zeros behind it year event. And it's been a long time since I've thought about this, but I think that is older than the age of the universe. Normal distribution, interestingly, is 75 million years. So if you fit a normal distribution, you get a 75 million year event, which I am interested in because the actual statistic quoted in the news was 7.5 million. So I wonder if I've made a mistake or they have made a mistake by an order of magnitude. And if you plot a skew normal distribution, you get like 9, 12, 76,000 billion years. So it's a 76,000 billion year event. But the point is that depending on the statistical distribution that you fit, these three curves that look almost the same, the green, the red, and the orange curve, you get repeat times that are literally billions of years apart. And that is why I think just saying this is a 7.5 million year event is not actually good statistics, because it's sensitive to the implicit statistical distribution that you use by tens of orders of magnitude. So yeah, we probably shouldn't do that. But on a closing note, I do think it is important that we find ways of communicating what an extraordinary year this is for Antarctic sea ice. And I think the sigma thing is like a bit abstract, and if you ask some guy on the street how likely is a 5 sigma event, they look at you really funny. So I have a lot of sympathy with the 7.5 million year event thing, and I just think I just have this like deep annoying urge to push back against the method through which that has been worked out. And I'm sorry about that, because I do think this, personally, I think, and this is not the consensus view of the scientific community, personally I think that this is a signal of climate change. And damn, do we need to do something about that.